Welcome to class, ladies and gentlemen. Here is yet another video from Mr. Eicher here. Happy Friday. Congratulations making it this far. We're in week 5. Next week on Tuesday, you'll have a quiz. Yippee. So to prepare for that quiz, I'd like to review 3 things. Number 1, using a sampling distribution to calculate a probability. Number 2, doing a 2-sample t-test. And number 3, doing a 2-sample z-test for a difference in proportions. Now that's basically the whole chapter, so let's hope and pray that this video isn't 196 minutes long. If it is, you would watch every minute, wouldn't you? You would. Be honest. You know you would. So let's jump in. Well, it's unnumbered, so numero 0. We have the electric light bulbs of manufacturer A have a mean lifetime, 1,300 hours, standard deviation 300 hours. Manufacturer B have a mean lifetime of 1250 with a standard deviation of 200 hours. If random samples of 75 light bulbs of each brand are tested, what's the probability that brand A lasts longer than brand B? To be able to answer this probability question, we're going to need the sampling distribution of the difference in sample means. And we have to describe the shape, center, and spread. This is a SOX question, shape, center, and spread. If you're ever asked to describe a sampling distribution, you're expected to hit the center, the shape, and the spread. So let's start with the center. We have mu x bar A minus x bar B. This notation means if you took one sample from A and another sample from B, found the means, and subtracted them, that would be one of those differences, x bar A minus x bar B. If you did that repeatedly for a bunch of different samples, and then average all of those differences, that would be mu. So what we know, hopefully we know, is this equals the mean of A minus the mean of B. Well, the mean of A was 1,300 hours and the mean of B was 1,250 hours. So on average, the light bulbs from A last 50 hours longer than the light bulbs at B. So our center is 50. We'll do the spread next. The spread, the standard deviation of x bar A minus x bar B equals. Now we have a special formula that we use with sampling distributions of the difference in sample means. And that formula looks something like this. Mega square root plus plus. And we have the sample standard deviation of A squared over n plus the sample standard deviation of B squared over n. So to calculate this, we would have the mega square root of, both sample sizes were 75, and the sample standard deviation of the A one was 300 squared, and the other one was 200 squared. And that would be how much our sample mean is expected to vary from sample to sample. And this equals approximately 41.63 hours. So we have a 50 and we have a 41.63. Lastly, we have the shape. Well, we're not told anything about the population shape of lifetime in hours, but we are told that both of these samples are 75, sample size of 75. So since both are greater than 30, vis-a-vis the central limit theorem, we could say the sampling distribution will be roughly normal. So we have a roughly normal sampling distribution. So how about we just include that right here? We have a roughly normal sampling distribution. Voila, I like the blue. We had 50 was on average the A bulb is 50 hours longer life. And then the standard deviation is 41.63. Really important number here is 0. 0 is an important number. So 0 is a little more than 1 standard deviation away. Here's 0. So anything on this side of 0, that would mean that A was lasting longer than B. Also known as A minus B is positive, greater than 0. Those are equivalent statements. Anything on this side, I guess, anything on this side of 0, that would be A minus B is less than 0, or also known as A is lasting not as long is less than B. The question that we're asked above in the stem of the question, what's the probability that brand A lasts longer than B? Well, just eyeballing this, A is going to last longer all of these times. I'll do a little shading there. All of those times A is lasting longer. So whatever our answer is, it better be pretty big. It's not going to be like a 5% answer or something like that. So to calculate that, so we're kind of on the next part below. You can scroll down on your paper. B says calculate that probability. Well, we basically have it all set up right here, surprisingly enough. We have, let's see, our lower bound. Right, there's our lower bound. So we could do probability that A minus B is positive. Actually, I kind of like it better if I did the probability that the sample mean from A minus the sample mean from B is greater than 0. I like that better. I think that's more accurate. Equals, well, we would do normal CDF. Normal CDF of, let's see, the lower bound is 0. The upper bound is infinity. The mean is 50. And the standard deviation is 41.63. Negative 1.2. So then we have the probability that Z is greater than negative 1.2. There. Now I've taken my own advice. Practice what you preach, I guess, as they say, whoever they are. So that is how to find a probability with a sampling distribution of the difference in sample means. I would think the hardest part is if the question had just said like that, what's the probability that one bulb lasts longer than the other on average? It would be tricky for students to realize that they need to find the sampling distribution and all this information. Okay, so that was the first part. Let's check out the next question. Ashton and Olivia wanted to know if generic chocolate chip cookies have a different amount of chocolate chips than name brand chocolate chip cookies. Change this on your document. On average. To investigate, they randomly selected 10 bags of Chips Ahoy cookies and 10 bags of Great Value cookies, and randomly selected one cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each. There were no cookies harmed in the making of this investigation. Here are their results. Chips Ahoy, blah, blah, blah. Great Value, blah, blah, blah. We have some summary statistics, and we have a dot plot and a box plot. How fascinating. So, question number 1. I think it might be nice. How about you pause this video and answer part A and B? There, wasn't that nice? So the first question, should we use a paired t-test or a two-sample t-test? Well, is the data paired? Is each cookie, like is this particular cookie, was it paired with this particular cookie? No, it doesn't seem like it. So I'm a little skeptical of the paired case. It seems like we have two independent random samples. Two independent random samples. The Great Value and the Chips Ahoy were not paired or matched in any way. So one way you can think of it is, if I change the order of these numbers, if I put like 18 before 17 here, are you going to lose some kind of connection between the two groups? No, not at all. You're still going to find an average of one and the average of the other. It doesn't matter what order that these numbers are. Now, if it were paired, then the order would matter. So for instance, if we were talking about like different students in a class and how they did on the first test and then how they did on the next test. So here are some students, here are their grades. First test, second test, 70, 90, ooh, nice improvement. Now if I switch these numbers, if I switch these two numbers, if I could circle things, and put 80 over there and 90 over here, then that's a lie. Student A didn't make an 80. Student B didn't make a 90. So you've lost a connection between the first and the second test scores. If shuffling the data like that messes up the means, then if messing it up causes a problem, then it's probably paired. Whereas up here, switching these two numbers doesn't particularly matter that you've switched them because they're not actually linked to these numbers below them. There's no link or association between those numbers. So you should have said, I hope, that we would use a two-sample t-test, not a paired t-test. It's an important question because the hypotheses will look different and the condition looks different. The normal condition, they only had 10 cookies. You see that here, 10. And both of those are less than 30, so we could say although 10, although both samples are less than, we'll say are small. How's that? Are small. 10 is less than 30. The graphs, I'm going to run out of space really fast. The graphs show no strong skew or outliers. So the sampling distribution is roughly normal. And that sampling distribution is the sampling distribution of x bar 1 minus x bar 2, if you're wondering which sampling distribution we're talking about. So that's the normal condition, and that's the two-sample t procedure. Next, you're asked to calculate the significance test statistic. All right, I'm ready now. I have the summary statistics and the question on a separate page to give myself a little writing room. So to perform a test of significance, first step, we have our hypotheses. Our null hypothesis would be the mu ahoy minus mu great value equals 0. That would mean where m, I'll write this here, m is the mean number of chocolate chips in a cookie for each brand. And if you use good subscripts like A for Ahoy and GV for Great Value, that's really helpful to know your order of subtraction. And then your alternative is mu A minus mu Great Value does not equal 0. The individuals are interested that there's just a different number in Great Value compared to Chips Ahoy. Okay, so that's our first step. We've defined our parameter. The conditions were met, so thank you very much. Next, we just need the test statistic. Let's do this two ways. number one, the very statistical way, we would have the t-test statistic equals mega fraction bar. We have the difference in sample means, Chips Ahoy minus great value. That would be 18.4 minus 19.4. That's our difference in sample means, minus the null hypothesis value, which is 0, divided by the mega square root, we saw this on the previous question, of both sample sizes are 10, and the standard deviation is 1.78, and the other standard deviation is 3.6. Can you notice my mistake? This is a common distractor on the multiple choice. They will see if you will fall for this answer option, forgetting to square and make them variances. To be able to add the standard deviations, you need the variances. So this test statistic equals negative 0.787. I guess I'll call it 79. Someone could double check my work on that, please. And we want to know the probability that the t-score, or the absolute value, is greater than 0.79. Since it's double-sided, it looks like we're going to have a rather large p-value. Remember, it's double-sided. Maybe I'll include a little sketch here. Remember, it's double-sided. Here's 0, since we've standardized. Here's 79. Here's negative 0.79. And we want this side or the other side. So we need to do 2 times TCDF, where we could do our lower bound is the 0.79. The upper bound is infinity, and the degrees of freedom, conservative degrees of freedom would be 9. So we would get a p-value of TCDF 0.79 to some large number, 9 degrees of freedom. That is 0.22, but we double it because it's two-sided. So we get a p-value of 0.45, basically. There's our p-value. Huge. 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 This is a wall. A wall that no one's going to cross. And it's a huge wall. So we would conclude that 0.45 is larger than any reasonable alpha level, but we were given 10%. We would fail to reject the null, HO, and we don't have not convincing evidence that there's a difference. And you can write context. I'm running out of space very, very quickly. But that would be, after all, I wrote it, but it is a really excellent solution, don't you think, with the formula and all that kind of stuff. Now, what I would recommend, actually, especially if you're not very good at memorizing formulas, rather than doing this, well, you're really going to do both because you're going to practice and you're going to get a 5 on the AP exam. But rather than doing this, you're going to do all that, and you're going to say, I'm going to use a 2-samp t-test on the calculator. So to review that, you're going to go to Stat. Scroll over to Tests. So Stat. Scroll over to Tests. And look for 2-samp T. Make sure it's a T test. And do we have the data or do we have the stats? Well, actually, funny you say that, we have the data, but I don't want to type in all that data. So I'm going to select stats. And I'm going to type in x bar 1 is 18.4. S1 is 1.78. The sample size was 10. X bar 2 was 19.4. The standard deviation of great value 3.6, another 10. Not equal to, never pool, and calculate. This gives me the test statistic, negative 0.79. That should look familiar. P equals 0.44. That's a little different because the degrees of freedom that the calculator can calculate for us is better than our 9 that we used earlier. It would be that, degrees of freedom. So, as long as you write this information, you can get out of writing the whole big formula that we wrote earlier. In some ways, I'm sad to tell you that because I don't want you to forget the formula. The formula you could see on the multiple choice. The formula is better statistical reasoning and a better communication, better response. But this way, for sure, like I've said in previous videos, saves time and possibly saves mistakes on messing up the formula, maybe forgetting to square the standard deviations. It definitely saves time, that is for sure. Don't forget to include your degrees of freedom as well as the test statistic and p-value. And we would come to the same conclusion that we did before. So that was part B. Part C says, construct and interpret why is that? Okay, I'm ready now. Construct and interpret a 90% confidence interval for the difference. Let's work with the formula, and then we'll see the calculator shortcut. The conditions are already met, so that's fantastic. The formula, if we're going to subtract ahoy minus great value, the formula would be the difference. Maybe we'll write the general formula first. The difference in sample means, that's our point estimate, that, plus or minus the t star times mega square root, I guess it's just t star, times the standard deviation of ahoy squared over the sample size of ahoy, plus the standard deviation of great value squared over the sample size of great value. So we would have, plugging the numbers in, we got 18.4 minus 19.4. Plus or minus, we'll get t star in a second. Mega square root, both are 10 sample size. And we had 1.78 squared, 3.6 squared. And then finally, this guy right here would be inverse t. Let's see, 90% would be 0.95, adding the tail, and then 9 degrees of freedom, which gives us 1.83. This would be the work that you'd show, or this would be the answer option you could see on the multiple choice. Let's get the answer, rather than with this formula, let's get the answer with our stat over to tests on our calculator. Scroll down for a little while down to 0. It looks like 2 sample z int. 2 samp z int. 2 samp. Oh, did I say z? How dare I? 2 samp t interval. You never use the z interval with samples because we don't know the population standard deviation. And since we just did a 2 sample t-test, my calculator, at least, I don't know about yours, my calculator stored all of the summary statistics already for me, which is beautiful. Oh, I just have to change the 0.95 from some other time to confidence level of 0.9. Pooled, as always, no. Calculate. And we get this confidence interval, negative 3.2, comma, 1.2. So, remember earlier we failed to reject. Well, here we're also going to fail to reject because 0 is inside this interval. So if 0 is in the interval, then it's plausible that the difference in number of chocolate chips between these two brands is actually 0. The difference is 0, meaning they have the same number on average of chocolate chips. Oh, did you hear that? That was my puppy Ebby shaking off her anxieties. So to interpret this, we would say we are 90% confident. Oh, maybe I'll highlight it. We are 90% confident that this interval captures the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. Plagiarism. Plagiarism. But that is how we would interpret the interval. Alright, so let's check out the last part of that question, which looks something like this. Does your interval provide convincing evidence that there's a difference? We already answered that. We said no, because 0 is in the interval. Alright, whew, marathon. Whew. Let's look at this last one. 2002, number 6, which says a survey given to a random sample of students at a university included a question about which of two well-known comedy shows, S or F, students preferred. The students were asked the question, do you prefer S or F? The responses are shown below. I learned from some of my AP Stats buddies that this question, whoa, where'd it go? This question was written based on actual well-known comedy shows, S or F. So I'll let you determine, can you figure out which two comedies from the late 90s, early 2000s do you think this question is referring to? But that's not actually going to be too bad. They don't ask like cultural questions on the AP exam, but I digress. Let's see, this is a question 6, so some interesting things might be going on. 6a says, construct and interpret a 95% confidence interval. So be really careful that you do both of those, construct and interpret. And we want an interval just for one proportion. So this is a one sample Z interval for P. So we don't need hypotheses when we do intervals, but we do need to check conditions. We have a random, was it? Yes. We have a random sample of students. The number of successes, proportion of students who would prefer S. So we would have, it would look kind of like this. N times P hat is going to equal to 10. Since this is an interval, we use P hat. And 1 minus P hat is going to equal to 10. This N times P is the number of successes, which is just 185, is greater than or equal to 10. And then this amount is the number of not S's, which would be F's, 139, is greater than or equal to 10. So the P hat distribution is roughly normal. Roughly normal. And then it's we assume it's a large university, so the independent condition is met. The formula that you would use is P hat plus or minus Z star. P hat, 1 minus P hat, over N. So this is a little review from Chapter 8, confidence intervals for one sample. So you can finish that question and interpret the interval. So if you need to pause this video to do that, that would be fantastic. Part B asks of this investigative task, what is the meaning of 95% confidence? Basically, they're asking you to interpret the level. What do we mean by this 95% confidence level? Your answer should say something about, in repeated sampling, 95 or about 95% of intervals will capture the true proportion of students who would choose S. So that's B, the meaning of 95% confidence. The last part, number C. In a follow-up survey, a separate group of randomly selected students was asked, do you prefer F or S? Now, it's easy to miss this. Do you remember what question was asked initially to the students? Initially, they were asked, do you prefer S or F? Now it's F or S. I think this might have been a little too sly by the exam writers. A lot of students didn't pick up on the difference in order. It does ask later, based on these two surveys, is there evidence that the stated preference depends on the order in which the comedy shows were listed in the survey question? It is important in surveys, when people don't really have a preference for something, then they might just pick the first option. So do you like candidate A or B? Like, I don't really care, A, because it's the first one. So they're interested to see, does the order of asking, S or F, F or S, does the order matter? So is there evidence? This is a significance test question. I guess you could argue you could use a confidence interval. But if we were to write hypotheses, the proportion who pick S minus the proportion who pick F would be equal. If there's no difference, it doesn't matter what order, then the proportions would be the same. Let me say that again. Said it wrong the first time. The null hypothesis. The proportion who picked S in the first group minus the proportion who pick S in the second group. Those should be the same if the order doesn't matter. The alternative hypothesis is the proportion who picked S in the first group minus the proportion who pick S in the second group, that it's different. Where the first group, they heard the S first, and the second group, they heard the F first. So, to review this material, some things to be careful about. When you check the normal condition, the roughly normal condition, you'll have to do n of the first group, which is 324, times p hat c. Is that greater than or equal to 10? Remember, p hat c is the combined proportion of successes, which we're defining as S, picking S. So that would be 68 plus 185 over 156 plus 324. So in the first group, 57% picked S. The next time when S wasn't first, it dropped to 44% picked S. What's the explanation for this difference in these percentages? Well, one explanation is just you picked a different random sample, so we're going to get different results, sampling variability. But the other explanation is, well, when S was first, more people chose it. When S was second, fewer people chose it. So the order of the question is changing people's responses. It's kind of a response bias type of question. So you can check the conditions. The other thing to be careful about is when you calculate your test statistic, you're going to have p hat S1 minus p hat S2 minus 0. But your denominator, remember, you're going to have that p hat c. So you have your first sample size, which was 324. You have your second sample size, which was 156. And the p hat c value you would get is 68 plus 185 divided by 156 plus 324, which is, looks like 53%. So this equals 0.53. So you're going to be using that value down here in the test statistic. So this video has gotten long enough, and it's actually 8:30 in the evening, which is past my bedtime. So I better get to sleep before I make any more mistakes in this video. So again, I just wanted to point out, as you solve this, as you complete this, make sure you check conditions correctly with p hat c, and make sure you calculate the test statistic correctly. I guess I could mention, rather than doing that test statistic formula and forgetting about p hat c, you could always use 2 prop z test and get the answers that way. And that would be a much safer and faster way to be able to answer this question. Thank you for watching this video. If you liked it, feel free to subscribe, like me on YouTube and Facebook, and follow me on Twitter. Enjoy your day.